Welcome to an overview of VEX Electrical Components. Let's take a look at the sensors that we have available to us first. So just exactly what makes something an input? An input is some type of sensor that brings us feedback about what's happening in our environment, or allows us to control things by what's happening, what is not happening, those types of things. Let's go ahead and break these sensors up into two different subsystems, digital and analog. On the left side of my screen, I have all digital sensors, and on the right side of the screen, I have everything that is an analog sensor. So what makes them different from each other? Everything on this side is really yes or no, provides me true or false type feedback. Everything on this side provides me things that are in a range of values, like how much light is there, not just whether there is light or not light, but in a quantity. So these are values that are in a range from 0 to some other number, depends on kind of the programming or the system that you're using. And these are all going to be yes or no. So let's go ahead and take a look at our yes or no digital sensors first. Okay, both of these sensors are very similar to each other. They're both yes or no type sensors. So when this one's not being pressed, that gives us a false signal or a 0. When it is pressed, that gives us a true signal or an on. So it's tactile, it's a touch sensor. So this allows us to know when something's here or not here. This one is called a limit switch. The bumper is basically the same thing, but rather than having just a lever arm on top that presses the button, this has a plunger on the top, or a bumper that we actually have to press. So it allows us to actually kind of come in from different angles and different sides to press it, but it's the same thing. This one is false when nothing is touching it, and is true when something is. Let's go ahead and break these two open and see if there's anything special that's actually happening inside here. So inside the limit switch is a very small micro limit switch. And you can actually see, if you open it up, that there's really only two wires that are getting used. The red wire itself is not being used at all. So most limit switches have three different wires that can go into it. We have a common, which right now is our black, and then we can have it normally open or normally closed. Normally open means that it reads a 0 when nobody's touching it, and a 1 when something is. So normally open means that it's false when nothing's up against it. If I had switched this white wire over to here, it would be considered normally closed. It would be reading a true signal right now with nobody touching it, and then a false or a 0 when somebody was up against it. So this red wire doesn't get used at all. So then why do they have a 3 wire on here? It helps us when we plug it into the Cortex, make sure that we're plugging it in the correct way, and it's just a lot simpler to not have to have a whole bunch of different wiring for the manufacturing process of putting all this together. But the red wire itself doesn't actually get used. We're only using the white and the black. Let's go ahead and take a look at the bumper. I'm going to take the cover off, and we can see that the bumper, or the button itself, is attached kind of to the cover. So it's loose inside here, and the important part really is this gold colored disc, this metal disc that's inside here. We also have a spring that's for the return, so that as you release the button, it's the spring that's pushing it back up. So where's the magic? The magic's actually inside here. It's these two little pieces of metal. So when I press the bumper down, I need that metal disc to touch those two pieces of metal and actually make contact with them. And when I make contact with those two pieces of metal, that's what closes the loop and allows us to understand or see that something's up against it. So to provide feedback, I need to press that metal disc up against those two wires that are inside there. So that's the limit switch and the bumper. The next sensor we're going to take a look at is the digital optical encoder. This allows us to put a drive shaft through here, and it allows us to count the number of rotations. Well, then you might say, well, then I don't understand how this is digital. I thought digital was supposed to be just yes, no, 1, 0, true, false type things. Well, that really is still what's happening. If I take the cover off of this, we can see down inside here that there's a disc with a whole bunch of tiny little slots in it. That's what makes it an optical encoder. So what happens is, as this little disc spins, it has the difference between places where it can read through the disc and then places where it can't read through the disc. So each time it goes through, it reads that as 1s and 0s. So each time it reads as a 1, it goes through that little slot, and then it becomes a 0 when it goes up against it again. What keeps it from counting? Well, it has to understand the difference between when there's actually a change. So it doesn't change until it actually rises and falls, goes from a 1 to a 0. You'll also notice that this has two wires going into it. So if this is just a yes or no type sensor, why are there two wires? Well, it is a little bit special, and it allows it to know which direction you're going. So each one of these wires allows it to know whether it's going clockwise or counterclockwise by which direction these little yeses and nos are coming from. So all we have to do is stick a drive shaft through here, and as it spins, it'll tell us yeses and nos. One experiment that you might want to do is figure out how many counts goes to one full rotation. So what I would suggest you do is go ahead and put a drive shaft through here, put a gear on there, and mark that gear. And as you do one full rotation, look inside the RobotC debugger window and see how many counts it actually takes to go into one full rotation. Our last digital sensor is an ultrasonic sensor. This is kind of like a bat. So this allows me to know how close something is and how far away it is. And it's the same thing as the last one. You may say, oh, okay, well, I don't understand. What makes this one digital? Why isn't this one an analog sensor? Because it gives me ranges of distances. Unfortunately, all it is yes or no on the signal that gets returned to it. So it actually sends out a sound wave. That sound wave bounces off of an object and then comes back. So a signal either comes back to it or doesn't come back to it. Once that pulse or that signal comes back to it, it takes the time or the range of time that it took for the signal to go out, bounce, and come back, and it converts that time into distance. So you actually can get errors. An error will happen if you send a signal out too far away that it'll actually degrade and not come back to it, or it's too weak when it comes back to it to get read. It could deflect off of an object and bounce off in kind of a strange direction and not return back to it, or it could get absorbed. Another thing is if you're too close. If you're too close and the sound comes out, it can hit an object, and then when it comes back, it might not come back into it. So the big thing you'll notice here is that we still have two wires, and this is extremely important on how you plug this in. One of them is an input and one of them is an output. The yellow one is an input. This is the microphone. This is the listening component of this. So they both look the same on each side, but they're not. So the one on this side is the microphone. The orange one is the output. So this one is the speaker that's going to send the pulses out. So the pulses are going to go out and then come back into the microphone. If you accidentally plug this in backwards into the Cortex, it doesn't work. You're going to be listening into the speaker and then trying to send signals out of the microphone, and it doesn't work that way. So I actually will convert one of these into an output and one of them into an input. So this is actually two different things. Currently, we only have three analog sensors. We have a photocell, or a light sensor. We have an infrared sensor, or they call it a line follower. And then we have a potentiometer. Let's go ahead and take a look at the photocell, or the light sensor, first. So you might see the light sensor a lot on things like night lights for bathrooms, or light sensors out for your street lamps to know when it's dusk or time to come on. In the middle of it, that tiny little thing, well, that's the whole sensor all by itself. That little sensor in there is a resistance sensor that allows us to determine the amount of light. So this one is truly an analog sensor. It will allow us to determine how much light is in the room and will give us some type of analog value. I would experiment with this, and I would cover it up completely and see what kind of value you get into the debugger window of RobotC. I would also go ahead and shine as bright a light on it as I can. Maybe use the flashlight on your cell phone to see what that range value is. The majority of the time in our programming, what we really want is a threshold. We want a difference between light and dark, or what it is right now, not an intense light, but the ambient light that's just inside the room, and then we can cover it up a little bit and see what it is for dark. So not completely covered up or concealed, but just kind of dark. The difference between those values is the threshold, and that's the range that we're typically going to use on whether there's light or dark. The next one we'll take a look at is our line follower. It is an infrared sensor. There's actually two things inside here. So just like the ultrasonic sensor, this is actually two pieces in one. There's actually an output and an input. So there's an infrared light that comes out of it, and then it has to reflect off of an object and then come back. It does have a range on how far away it can read, but it's infrared, so it can kind of see in the dark. The nice part about this infrared signal is it actually will give us an analog value. A good portion of your IR sensors out there, or infrared sensors, really are just yes or no. The signal either returns to it or doesn't return to it. But this one will actually give us a range and almost allows us to read color, at least in a grayscale type environment. So we can kind of tell the difference between something that's yellow, red, black, things that have a high difference in the grayscale value. It has a hard time telling the difference between something like yellow and light blue. Those types of things, because it can't really see color per se, but it can give us a different range value. So a lot of times we'll use this as a line follower. So if I've got a white table with a black line on it, then I can tell the difference between when I'm on the white and when I'm on the black. And the last one that we have is our potentiometer. The majority of the time, the potentiometer doesn't look like this. Most of the time when you think of a potentiometer, most of us think of this type of potentiometer. We'll see them a lot in like bathrooms where you have a dial that allows you to determine how much light is going to be in the room, whether it's going to be a really bright light or a dim light, those types of things. But this one actually gives us the ability to, same thing, put a drive shaft through here. And as we put a drive shaft through here, then we can tell rotation. Now, if your potentiometer is still good, you should actually feel limits on here. So if I turn this potentiometer, I should feel it come up to a stop. And then if I twist it the other way, I should feel it come up to a stop. If I don't, then unfortunately this potentiometer may be damaged. So it won't actually have full rotation all the way around it. The majority of the time it'll read a distance or a degrees between 0 and somewhere around 265 degrees-ish. So it can't go all the way around or have a full rotation. But we can use it to accurately position a motor in specific locations or tell how much of it has turned. So I can use it in similar situation as the optical encoder, but the optical encoder can go full rotations, multiple rotations, where the potentiometer cannot. But the potentiometer is extremely accurate as far as trying to get something in a specific location. So now that we've taken a look at all of our inputs, let's take a look at the Cortex and see how they all plug in. On this one side of the Cortex, this is where my digital and my analog sensor are going to plug in. And you have to make sure that everything plugs into the correct port. So if we actually take a look at something like the limit switch, when I take the limit switch and go ahead and plug it in, you want to make sure that the black wire always goes to the outside. So because this is a digital switch, and that's why it was important for us to categorize it, I can plug it in anywhere from the 1 to 12. So all I have to do is slide it in and make sure that all 3 prongs go down into the Cortex, and that's it. So right now I have this plugged into digital 1. So black wire goes onto the outside, and your digitals can get plugged anywhere between 1 and 12. So you have 12 different digital sensors that can all be plugged in at one time. Your analog sensors work the same way. You have the black wire that's going to go onto the outside, and they can go anywhere from 1 to 8. So I can just take it and plug it in, make sure that all 3 go in all the way, and that's how you can plug in your analog sensors. Remember, the ultrasonic is digital, but you have to make sure that it gets plugged into the right orientation. It has to be 2 ports right next to each other. So it can be in port 1 and 2 or 2 and 3. However it is, you have to make sure that the yellow goes in first and then the orange. So my yellow would go into 1 and my orange would go into 2, so that I have my microphone and my speaker. The quadrature encoder really doesn't matter. It just has to do with whether it reads clockwise first or counterclockwise. But you can plug these in any order, but same thing, they have to be plugged into 2 ports right next to each other. So it'd have to be like port 1 and 2 or port 2 and 3. So that's all of our input sensors. Let's go ahead and start taking a look at all of our outputs. So these are the outputs that we have available to us. We have 2-wire motors. We have servos. We have a flashlight that's LEDs that we'll get to here in just a second. And then we have these small little LEDs that can get plugged into the Cortex. So all of these produce some type of results. They all do something. So I can turn them on, I can turn them off. So on and off the flashlight, on and off the motor. I can control how fast the motor is spinning. Servo, which we'll deal here with just a second. And then the little LEDs I can turn on and turn off. If you have an older VEX kit, you might also have one more motor. So it's another 2-wire motor, just like this one. This is a 393, or is the big motor, and this is a 269, or the small motor. So the older VEX kits came with 2 different size motors. The new ones just come with the 393. So let's start looking at the motors themselves. So what really makes this motor special? Well, I've got a broken one here that I've gone ahead and opened up so we can take a look inside it and see if there really is anything special going on. So if I open up the green cap, I can see that I have a set of gears that are inside here. These set of gears actually gear down the motor so that it's not running as fast as it could be running, and allows us to have a lot more torque out of the motor. So the gears on this side just basically are part of a gearbox that allow me to get more power out of the motor itself. On the other side is the actual motor itself, and then the gears that decide how fast it really is going to run. So the majority of these gears, these motors, actually come with a replacement set of gears. So I can take this bearing off, I can take these 2 gears out, and I can replace them, and I can make this a high-speed motor rather than a low-speed motor. So I lose torque, making it a high-speed motor, but these 2 can be replaced and swapped out for some other ones. So I really don't ever need to be in the green side. I just need to take off this front side to be able to get at these 2 gears themselves, and they're fairly easy to replace. But the motor itself is just a simple, small DC motor. And again, it runs really, really fast when it's plugged in. So the gears that are on the other side are gearing this down anyways. And then the 2 gears that are on this side are actually the ones that we can use to control the speed. So that becomes our high torque, low speed, and then there's another set that allows us to go low torque, high speed. So these 2 run all the time. So you've probably seen other type of regular DC motors. This is just the same thing. So it's just a small DC motor that's inside here that's running inside this cabinet, and then the gears allow us to control how fast it goes and how fast it spins. The other 269 is the exact same thing, just has a different set of gearing and a smaller motor that's inside there. The nicer part is it's extremely light compared to the 393. So the 393 is a fairly heavy motor. It's got a lot more power to it. The 269 is a lighter motor, and I can use it in smaller applications like on the end of a gripper, so I don't have so much weight to lift up, but it doesn't have near as much power to it. So that's the 2 motors that you have available to you. So here's our servo, and this may look like a motor, especially like the 269s, but it's not. It really is a special motor. And how can you tell the difference between this and the motors? Well, one, it actually says servo on it, but this one has 3 wires, which we'll get to here in just a second. So what makes this not a motor, but kind of a motor? This doesn't have full rotations. A servo actually can only go about 100 degrees. And that's it. Well, that doesn't sound very useful. It's positionable. So I can actually tell it to rotate to a specific angle, and it will hold that position for me. So this is really nice for doorways or things that are going to open to specific values and rotations. So what makes this one so special, and how does it work? So I had a damaged servo that we'll go ahead and open up and take a look at. So it's the same thing. On the green side, I just see a circuit board. So there's all kinds of circuits and whatnot that's actually happening in here. So that makes this one a little bit different on its own. It really is the same thing as the special part is on this side. And I can see that I have mostly plastic gears. And the only time I would replace them is if one becomes damaged. But this black gear really is the special one. So if I take this black gear off, underneath here is a potentiometer. So that's what makes this servo work. So when you turn on the motor, unfortunately I can't control its speed. It just runs at one speed, but it will rotate and it will turn this potentiometer. And as it turns this potentiometer, it allows me to read that value. So when I say I want this to go to 127 or whatever number it is, it will turn this motor on. The motor will rotate until it has turned this potentiometer to a certain value. When it does, then it stops. So this can only go to a specific amount because it's just like our old potentiometer. It only has a range. So if I actually rotate this, I can get it to go to a point to where it stops. And if I rotate it, I can get it to a point to where it stops. So that's it. It only has the same limitations as our regular potentiometer does. It doesn't have full rotation to it. It goes to a place and stops. There's actually a physical piece inside there that actually stops it. So if we want to actually compare this or equate this out to something that we've got, then you really have this. You have a motor with a potentiometer on it. So when I turn that motor on, it will turn the potentiometer. As soon as the potentiometer reads the value that I'm trying to get it to, then it stops the motor. And then the same thing. So it can go clockwise and counterclockwise, but it'll only go until it gets to a position and then stop. So this is what a servo is. A servo is a potentiometer and a motor. Next is our LEDs and our flashlights. The LEDs we'll get to here in just a second because they're a little bit special. But the flashlight itself, there's a couple things. Number one, know that it has an on and an off switch. So if your flashlight's not working or not coming on, make sure that you have it turned on. The other thing is this is also a 2-wire, and because it's an LED, if you plug this in backwards into the Cortex, then it won't do anything. It won't work because it is a diode. So just because your flashlight's not coming on doesn't mean that the flashlight's damaged. It may mean that it's either plugged in backwards or it may mean that it's off. So that's two things you want to check if your flashlight's not coming on the way that it's supposed to. The LEDs are actually kind of special. Because they're such low voltage LEDs, they're actually going to get plugged into a completely different port. If you accidentally plug these into the normal port where we plug in the rest of our outputs, unfortunately these LEDs last, I don't know, a second or so, and then after that, then they're damaged and they don't work anymore. And unfortunately, they're not like a normal light bulb where you can look at them and kind of see that they're burned out. Because they're LEDs, the only way to know that they're burned out is to plug them in and turn them on with the Cortex, and if they don't come on, then they don't work. So that's the only bad part about them, is they can accidentally easily be plugged into the wrong port, and if they do, then they're easily damaged. Now that we've taken a look at all of our motors, let's make sure we know how to plug them in. The same thing as it was for the inputs, I try to make sure that I always plug the black to the outside, but that doesn't always have to be. So one big thing about motors is as you plug them in, black on the outside, if you actually pulled it out, turned it around, and pushed it back in, that would make the motor go the opposite direction. So I can control the direction of the motor in programming, and I can also control it into hardware. I typically don't. I'd rather control it in the program itself, but if it came down to it and I absolutely need to do it really quick, then I could pull this out and swap it. So the majority of the time I keep the black on the outside and red on the inside. Okay, so there's a big difference on these. You have 10 ports that you can plug into, but 1 and 10 are designed to take a 2-wire motor and plug directly in. So both your 393 and your 269, they can be plugged directly into port 1 and 10, but no others. So that doesn't make sense. Why do I have so many motor ports, but these can't get plugged into it? Well, they can get plugged in. You just need one more special piece. So you have this motor controller that allows you to take 2 wires and turn it into 3 wires. So this is how you're going to use port 2 through 9, even with the flashlight. So the flashlight can plug into any of these as well, directly into 1 and 10, but it can't plug directly into the rest of them. If it is, then you can't control its on and off. The only way you can do that is with a motor controller. And same thing, because it is polarity sensitive, you need to make sure when you plug this in that you plug black into black and red into red. So now I can take this flashlight and I can plug it into any of the other ports, so 2 through 9. So this motor controller is actually something extremely special. The special thing about these motors is you have to understand the way to control the speed of these is done by PWM, or pulse width modulation. Let's jump over and take a look at that. In this picture, you can actually see an example of what PWM is. Our motors are actually always receiving voltage. They're receiving voltage all the time. It just has to do with space that is there. So if you look at this chart, you can see a voltage versus time in what's called a cycle. So one specific cycle depends on how much of the voltage is actually on and then how much of it's off. So if we're at 25% duty cycle, or 32 in our Cortex, then that means 25% of one cycle, I'm sending it 7.2 volts. The rest, or the other 75%, I'm not sending it any voltage. So I'm sending it as 25 on, 75 off, 25 on, 75 off. That is giving it voltage, but voltage with a gap in it or a space in it. That's what's actually making the motor run slower. So at a 50%, then you're 50% on and 50% off for each cycle. And that's the way it continues to send it. So it actually is getting voltage all the time. It just has a small amount of space in there when it's not getting it. If you put a voltmeter on it, that signal is actually happening so fast that the voltmeter would actually show 7.2 volts all the time, or whatever voltage is coming out of your battery. The only way to actually be able to see that is plugging into something like an oscilloscope that actually show me the actual voltage itself and see what it physically looks like. A 75% duty cycle, which would be 95 on our Cortex, would be 75 on and 25% off. And when we're sending it the full 127, then we're giving it 7.2 volts or full battery voltage 100% of the time. And that's why this motor controller is so important. If I don't have this motor controller plugged into port 2 and 9, then I can't control the speed of these motors. These motors only have power wires. They have the black and the red wire. It's this third wire that's here that allows us to actually control the pulse width and allows us to control the speed for all three of these. The last piece is the LED, and as I said, don't plug it into the motor ports. It actually is going to get plugged into a digital port. So as I come over, and it'll only plug in one way, so the two little prongs are going to come into here, or into the middle of it. So as that gets plugged in, I'm going to have to go into the motors and sensor setup inside RobotC, and I'll change this port from an input to an LED, and that'll turn it into a low voltage output that can turn on these little tiny LEDs at a voltage that's not going to damage them. So that's all of our inputs and outputs. I encourage you to explore and play around with them and plug each one of them in and see what you can make them do.